That's quite simple. The F1 dot is the F1 times the cosines. Okay, F1 is here, times the cosine of the wing of the angle of rotation between the two coordinate systems, plus the F2 times the sinus of the rotation. And the other one, F2 dash, is minus F1 sinus theta plus F2 cosinus theta. Okay? Very important to realize is that the vector is the same. For example, I mean, all I've done here, if you want to consider the wind which is blowing, the velocity of the wind is a vector. If I want to give this vector in geographical space or in magnetic space, magnetic north is not the same as geographic north. There are two vectors. Of course, the wind doesn't care what kind of coordinate system we use. The numbers change, but the vector doesn't. Special coordinate systems. If I rotate my coordinate system so that the x1 double dash is like this, then of course one of the component will be the maximum. It will be the largest x1 component, and the other one will be 0. Okay, so there are, for these kind of coordinate transformations, some special orientations. Orientations in structural geology are everywhere, and you have to be able to measure orientations. I hope that most of you have already had a geological compass in your hands, and you have been able to measure a plane. So for example, here is your plane. This is the dip line, this is the dip direction, and this is the dip angle. So for example, if you would write, this is the European notation, if you would write 212.47, that means, and that this is a plane, that means that there's a plane which the steepest dip dips to 212, which is a little bit to the southwest, and it dips 45 degrees from horizontal. Okay? Now, if it's a lineation, and it's 212.47, then what we mean is a line of which the projection to the horizontal goes to 212, and the angle between horizontal and the line is 47 degrees. If we want to, for example, calculate angles between two planes or two lines or intersections, then you can use the stereo net, which you have all learned in the previous lectures. But you can also use vector algebra to compute. And if you have to compute the intersection of 5,000 planes with 5,000 other planes, then I don't think you want to use a stereo net. To do that, we have to transform this kind of notation into a Cartesian coordinate system. Okay, and I think that this has also been shown to you before. It's quite simple. This is north, east, and down. And if we have our vector, then we can calculate the 3-component, the 1-component, and the 2-component of this vector from these two directions that are given here. On the website of the course, there is a Excel sheet which we are continuously improving, and it has actually all these little formulas programmed in it. So if you want to play with it, put in some numbers, explore how it works, please feel to download it and try it. So the homework, if you want, for this particular lecture would be to explore the spreadsheet. I'm afraid that the exam is going to contain a number of these kind of calculations, so I would strongly recommend that you actually do it and learn how to do it. Typical exam question would be multiple choice answers to intersections or calculations with vectors. Okay, once we have used our planes and once we have used our lineations to put them into Cartesian coordinate system, then we can start doing all kinds of magics. And the two important formulas here are the scalar product and the vector product. Of course, you have all learned linear algebra a little bit, so this must be quite familiar. The scalar product you can use to calculate the angle between lines. The scalar product of two vectors is the length of the first vector multiplied by the length of the second vector times the cosine of the angle between the two. So if you want to calculate the angle between two, you just take the scalar product and divide it by the length of the one and the length of the other. Very, very simple. The vector product is a vector. That's why it is a vector product. It is also called the cross product. And the vector product is a vector which is perpendicular to both of the other vectors. So if I have two vectors, this one and that one, then the vector product is a vector which is perpendicular to 2, and the length is this one times the sinus of the angle between the two vectors. So for example, if I have two planes and I want to calculate the intersection of these two planes, it's very simple, because all I have to do is I have to take the normal to this plane, I have to take the normal to this plane, and I take the vector product of those two, and that is my intersection. Okay? So vector are behind all these stereo nets. There are many stereo nets programs on the internet. You can program them yourself. It's not very difficult. And most of you are now learning to use these stereo nets to work with orientations. A very simple example. All these points represent planes. Okay, each point is a plane. It represents a normal to the plane plotted in this stereo net. And if the points fall on a great circle, in German it is called the Pi-Kreis, that means that the structure that we have out of these layers is a cylindrical fold. Maybe I can borrow your book. One moment. Okay. If you have a structure like this, then all the different layers on this structure give you this diagram. This great circle again has a pole, and that is the axis of this fold. Now, stereo nets are very useful because they allow you to analyze certain geometries, but one thing that they do is they take away the spatial information. So in this particular stereo net, I don't know where the data come from. Everything is plotted in one net. So this structure here and this structure will give you exactly the same stereo net data. By putting it in a stereo net, you gain a certain amount of information, but at the same time you lose something, you lose the spatial information. So data in stereo net are rarely completely conclusive about how the structure works. But for example, you can get out of your stereo net that you have a fold and then go back and plot it in your profile. The same story holds for this. you cannot distinguish an anticline and a syncline from just the stereo data, because you don't know where the measurements are. But very important in structural geology, and these kind of diagrams will come back over the course of these lectures, and in the tutorials you are going to do quite a lot of exercises. Next year's advanced structural geology course, there will be more of these exercises. It's all about understanding the patterns in the stereo nets. So for example, here, this is a partial great circle. These points lie on the great circle, but they don't sit everywhere on the great circle. Therefore, the folds that we have are not completely round. It is just an arc like this. Okay? This one goes all the way around, and then the great circle is completely taken. If the data lie very closely on this great circle, then this structure is very cylindrical, if you want. It is, can I borrow your book again? It is very smooth, if you want. If the data don't lie so closely, like this, on the circle, that means that there are a lot of wobbles in the structure. There is not so clearly a great circle defined. There are more complicated things like clusters of data. That would mean that my fold is very sharp. It just has two straight sides. And for example, this one, you get these small circles when some of your elements of your structure are lying on a cone. Okay, so it is now not a cylinder, but a cone. And there are very nice examples in structural geology where you can recognize these small circles and use them for your analysis. Okay, so this is the first lecture. I have given you some administration information. If you want, get in touch with us, sign up to the website, and you will get a password. I have told you the information about the exam. If you have any questions, then please ask us or ask us one of the Hiwis. And then I told you about what is structural geology, how you can get a job as a structural geologist. I told you something about models, the geometric models, the kinematic models, the dynamic models, and then we started to work with vectors, coordinate transformations, vector operations, and I show you some examples of the stereo nets. So, next time we will start to think about strain. Bye-bye.